Hello everyone, welcome back to the Heterogeneous Parallel Programming class. We are at lecture 4.4 and we will be introducing the next important parallel computation pattern, scan, and also called prefix scan in the literature, prefix sum. The objective of this lecture is for you to master parallel scan or prefix sum algorithms. And scan is frequently used for parallel work assignment and resource allocation. For those of you who write operating system or dynamic runtime, you will be using this kind of algorithm for parallel work assignment and resource allocation quite often in the future. And also, it is a key primitive in many parallel algorithms to convert from sequential computation into parallel computation. A lot of times we have work or computation that would need to be step by step, and the next step builds on the current step. And scan is a method for converting this kind of sequential stepwise algorithm into parallel algorithms. Therefore, it is a very important foundational parallel computation pattern, and it also offers a great opportunity for us to further understand work efficiency and performance trade-offs in parallel algorithms. For those of you who are interested in reading more about parallel scan, there's a great article about, by Mark Harris at NVIDIA, and I'm giving you a link to the PDF file for that article. So mathematically, prefix sum or scan is defined as either inclusive or exclusive. So here I'm showing the definition of an inclusive scan. The inclusive scan is a mathematical operation on a sequence of methods, numbers, x0 through x minus n minus 1 in this example. And when we apply scan to the sequence of numbers, we'll generate another sequence of numbers. And each element of the new sequence is the cumulative application of that operator to all the previous input elements. So for x0, it's going to be just the zero's output is just x0, but the output 1 is going to be x0 operate x1, and so this is a cumulative operation operator application from x0 to x1, and we will keep going until the last one. So for the last one, it's going to be the application of the operator to all the elements in the input sequence. So as you can see, this is a cumulative application of that operator to all the elements up to the current position in the output array. So a concrete example is that we can do an addition operator on a sequence. So if we use addition, the scan is going to be applied with these addition operators. And let's say if the input sequence is 3, 1, 7, 0, 4, 1, 6, 3, and then the application of addition scan to that sequence will generate a new sequence. And the first zeroth element is just 3, and the first element is going to be just the addition of 3 and 1. So up to that position, and that gives us 4. And then the next element is going to be the addition of 3, 1, 7, and that's going to be 11. So every element is going to be just a cumulative sum of all the input elements up to that position. And because the input is going to be, because all the elements are going to be included in that accumulation, if we look at the last result, all the elements in the input sequence are in that accumulation. So we'll call this an inclusive scan. So let's look at some practical applications of parallel scan. So let's say if we have a kind of a toy problem where we have a 100-inch sausage that we would like to distribute to 10 students. And so we ask each student how much the student would like to have. And then some of the students are hungry and some of the students are not hungry. So the first, the 0 student asks for 3 inches, the next student asks for 5 inches, and then 2 inches and 7 inches. One of the students is very hungry, so she asks for 28 inches, and then 4 inches, 3 inches. One of the students is not hungry at all and say, I don't want any. So here is the sequence of all the desired amount of the students for the sausage. So the question is, how can we cut the sausage quickly so that we can give the sections that each student wants to the students? And also, oftentimes we'll ask, how much of sausage are we going to have left? So there, in general, 2 kinds of methods that we can have. The first method is sequential. So we can easily just take the sausage, starting with the 100-inch sausage, and then we take the order from the first student, 3 inches. So we measure 3 inches from the beginning, cut. And then, the remaining remaining sausage would serve the 9 student, remaining 9 students. So we take that second order, 5, and now the beginning has already already accommodated the first student. So we take that remainder section and we cut 5 inches, and then we take the remainder section, we cut 2 inches, and we cut 7 more inches, 28 inches. So each time we cut a section, we give it to one of the students, and then we cut another section, we give it to another student. This is a very simple method. Any time when we take the remaining section, we just need to measure the next order. We cut, we give to the student. This is a very simple method, but it can be very slow if we have 1,000 students waiting for their sections. So in general, we would like to be able to parallelize this cutting process so that we can serve a large number of students in parallel. So what we can do is, after we get the order, we have the 3, 5, 2, 7, and so on order, we can do a parallel scan on this sequence and generate a new sequence. So we will get 3, 8 is 3 plus 5, 10 is 3 plus 5 plus 2. So these numbers are the cumulative order amount of all the students up to this position. So these numbers give us the positions that we should cut in the original sausage. So the first cut should happen 3 inches into the sausage. The second cut should happen 8 inches from the beginning of the original sausage. And then the third cut should be 10 inches into the sausage, and so on. So once we figure out all the cut locations, and we can simply take a large number of knives and then aim each knife at one of these positions and do a parallel cut. Once we apply that parallel cut, we have the sections for all the 10 students. And in fact, if we need to ask how many inches are left after we cut the sausage for all the students, we simply need to subtract 61, the last number, from the total 100, and that gives us 39 inches left. So we even before we do the first cut, we can easily figure out that we will have 39 inches left after we cut, we serve all the students. So if we can do that scan computation fast, then we can parallelize the whole process extremely fast. So that's the reason why parallel scan is an important computation for many, many parallel algorithms. So what are the typical applications of scan in our computation applications? Well, scan in general is a simple and useful parallel building block, and it will convert recurrences from the sequential form. Oftentimes, we'll have some kind of sequential loop in our application. So this is a sequential loop that loop from j equal to 1 to j less than n. So, and then for each output, we're going to, the output is going to depend on the previous element plus a function value that's related to j. So if we look at this loop, it seems like we have a very strict sequential computation where output element j is going to be depending on the previous output element and so on. So we have to compute all the previous output elements before we can compute output element j here. And each iteration, we do a function evaluation, and then we do the accumulation. So, but if we have parallel scan, then we can convert that sequential computation into a parallel operation by evaluating all the function instances of f with all the j values. So we assign all those function results into a temporary array temp here, and then we do a parallel scan with temp as the input, and then we put the result into the final output array. So this gives us a very good way to parallelize all the function invocations, and then hopefully use a parallel scan to quickly generate the final output result. And this is in general much more useful for many sequential computation than many other alternative methods. So if we are familiar with carry look ahead adder in hardware design, it is essentially a scan algorithm, and it generates carry. Every bit position generates a value and then carry position. So all the higher order positions depend on the cumulative results of all the previous positions. But carry look ahead is really a scan method that quickly generates some of the values, so that we can easily generate an add result with minimal delay. And for software development, we use parallel scan algorithms to implement parallel versions of many core algorithms, such as radix sort, quick sort, string comparison. This is frequently used in data mining, and then lexical analysis and stream compaction, polynomial evaluation for numerical packages, solving recurrences and tree operations, and histogramming. So as we will see that it is truly a foundational pattern for parallel programming. So there are also many other related applications. In real world, we oftentimes could use scan for something like campground allocation or farmer market space allocation. A lot of times when you go to farmer market, you see that some of the farmers require a small storefront and some of the farmers require a huge storefront. So what we can do is, just like a sausage cutting, we can have each farmer to put in the requested amount of storefront in a farmer market, and then we do a parallel scan. We can assign the location so that all of them can just go to a assigned beginning location, rather than having each of them to take up one storefront before the next one can take the front. So this can make the farmer market start up on Saturday mornings much faster. And as we can see, many of the computer science and computer engineering concepts that we teach in these classes actually can apply broadly to all kinds of logistics and so on in real life. We oftentimes use scan to perform parallel memory allocation to parallel threads. When we have a large number of threads all need memory allocation, we oftentimes can just use the request amount for each thread, do a parallel scan, and then assign all the space to all the threads in parallel. We can allocate memory buffer for communication channels in high speed, communication switch network switches for the same reasons. So let's go back to the algorithm aspect of scan. So let's say we're going to be using addition scan for the rest of our course. But you can easily apply the same methods to maximal scan, minimal scan, and product scan, and so on, and or any of the functions that you define as operators. So here, with for addition scan, the operator is addition. So we essentially have a requirement where we're given a sequence x0, x1 through xn-1, and we want to calculate output, which is y0, y1, y2, and through yn-1. And so such that y0 is the same as x0, y1 is x0 plus x1, y2 is x0 plus x1 plus x2, and then yn-1 is x0 plus x1 plus x2 all the way through xn-1. So we can easily use a recursive definition of yi equals yi minus 1 plus xi. And this is a very common recursive definition of this sequence. So we can write an efficient C implementation for a sequential implementation. So we can start the by assigning y0 with x0 value. And then we can go through a for loop where I will go from 1 to max I, which is n in the previous slide. And then we can, for each iteration, we will calculate yi by adding yi minus 1 to xi. And so this will give us a very simple iterative method for generating all the yi values. And this method is extremely computationally efficient because we only need to do n additions for n x input elements. So this is an order n linear algorithm. And computationally, this is as efficient as the reduction sequential implementation we mentioned before, even though we're generating a whole lot more output values. So the only reason why it's more expensive than sequential reduction is because we need to use a output array, rather than just single output value. So we will be doing more memory accesses when we generate all the y values. So it's slightly more expensive, but not a whole lot more. And computationally, they have equivalent algorithm complexity as the reduction sequential algorithm. So now we are ready to look at how we can do inclusive parallel scan and algorithms. So here we show a naive inclusive parallel scan. And we can assign one thread to calculate each y element. So it's very intuitive. We have one thread in charge of to be in charge of generating one output element. And so thread 0 would do y0 equal to x0. Thread 1 would do y1 equal to x0 plus x1. Thread 2 would do y2 equal to x0 plus x1 plus 2. And so this is very parallel. Every thread can do the computation independent of others. But if you look at this algorithm and you think about it a little bit, it is truly naive. It's actually ridiculous, because what's happening is that if we do this algorithm, when we come to yn minus 1, it actually needs to do all the additions that the sequential algorithm would be doing. That single thread is going to be doing all the additions of all the x elements. And so it will take just the same amount of time as the sequential algorithm for that last thread to finish. So this parallel algorithm is not going to be finishing any faster than the sequential algorithm, and meanwhile it's consuming a whole lot more execution resources. So if we're just doing parallel programming for the sake of being able to do parallel programming, we can write things like this, but it's not going to do anyone any good. So this goes to a very important quote that I always make to my students. Parallel programming is easy as long as you do not care about performance. However, the very reason why we're doing parallel programming is because we're trying to accomplish higher execution speed and more, better, performance. So we're going to go into the next 2 lectures to see how we can do much, much better than this kind of naive, ridiculous parallelization. So this brings us to the end of the lecture. And for those of you who are interested in learning more about scan computation and parallel scan, I'd like to encourage you to read sections 9.1 and 9.2 of the textbook. Thank you.